It's Vintage Thursday. This time I have quite an old VCR. This is a mono forehead machine by JVC that was dug out of a basement and didn't work. So the guy that owns it asked me if I could have a quick look at it and see if I can get it going so that he can transfer some of his tapes over to digital. So let's get started. Got an old VCR here. This is a very old JVC. I'm told it doesn't work. So let's see what the problem with this one is. So it's sounds like it's playing the wrong speed. So this could be something as minor as a dirty control head, or it could be something more complicated like a problem in the servo circuit. So we'll find out once we get into the machine itself. This one's got a linear power supply in it, and it's got some like circuit glue on here too, which I don't think that's the issue. But first, let's try cleaning the heads, see whether that'll solve the problem. So to get it to the heads, remove a couple screws here. And the circuit board will flip out of the way. Video head, that there is the grounding electrode. If you have white specks on your screen, suspect that. We'll do a demo on that if we can get this thing to work. Audio control head is over here, so first things first, let's clean the audio control head. Clean the video heads. Yeah, it was, I would say, there was a fair bit of dirt in there. I got a big wasp in here. Wonderful. We just shoo him away. We'll do the same to clean the video head. Piece of paper. Yeah, a little bit of dirt on there. Okay, we'll try this again. See if it works.
Have a problem getting rid of the ink. Hand cleaning and skincare is a daily activity.
Well, this time it
every industry and every field
seems to be playing the correct speed, but it's certainly not tracking properly. And now, okay, now we're back to the wrong speed again there. So I have to think we've got a problem in the caps and servo circuit, maybe the control track circuit. So let's look at the control track and see if we've got a signal coming off the control track head. Control track is right here. I believe this is the line here. This is the plug that the control track head is connected to the board. So let's scope it and see if we've got any signal coming off the head. So I clipped onto the head. This is the control track head. I'm not getting what I expect to see, which will be a nice even pulse, and I'm not seeing that. If I stop the tape from moving, this looks to be more random noise. I should see a pulse there, and I'm not. So we have a problem in the control track circuit. Either that or the head is bad. The level coming off the head though is very low. It's hard for the scope to measure it considering all the noise that's around here. That noise that I'm seeing incidentally is coming from my plasma TV. If I turn off the plasma TV, that noise goes away. Let's measure the head to see if there's continuity. 273 ohms, 272.8 ohms. So the head is not open, that's for sure. I'm going to try again, this time without the plasma set turned on, because I'm getting a lot of noise and it appears that that's what the noise is coming from. So damn plasma TVs, right? Cause so much static or so much interference. There's the head there. I'm still seeing a lot of noise though from other things in here. Capacitor here, C402. Whoops, my head in the way. C402 is across there, and then there's the signal comes down this way. C407. Somewhere in here, I think. This should be the preamp, I think, for the control track head. And I don't see any signal. I just see the noise. Not the same noise I was seeing before. Whoops. Well, did you see that? Ooh, hit the tape. So we know everything in here is good. The circuitry here is good. So I'm just going to take a look and see where that head plugs in here. So this is the CN401. And if we trace CN401, looking for something which to point with, this will be good enough, I guess. So CN401, there's C402, which is right across there. It's a capacitor across the head. That would be to bypass any high frequency noise. So technically that could short. There's C407, which is down here. This is an electrolytic capacitor, and then there's R401, so the signal goes this way through C401, and then there's a couple diodes here that are used to clip the signal. It looks like one side is going to the cathode, the other side is going to the anode of these two diodes. So they're clipping the signal and providing a rectified signal passing through to here. So that wouldn't be the way it's going. The other way it goes is it goes through C407 through this resistor, and then from here it goes down into, it looks like it's going into that pin of the IC. That pin should be the input. So this is where I would expect to see a pulse going in, but there's nothing. There's nothing coming in from the control track head. So I gotta think it's one of these components in here. It's either going to be, I think it's going to be a capacitor more than likely, but it's either going to be this one over here shorted, possibly this one here, or even maybe even that one over there. But I think we're going to have a shorted capacitor here. I'm going to power this unit down, and let's just measure. I'll unplug the head so that we don't look at the continuity of the head and see whether we have a short across the plug.
CN401 1.7, so we don't have a short across the plug here. Interesting. So that capacitor is definitely not shorted. This resistor here is 670.
Let's see what value that one is.
And there's a capacitor here. No short there. How's our capacitance? Now I know I'm measuring it in circuit, so I may not get an accurate reading, but
50 microfarads. It's probably a 47.
Is that what that is? That's a 47 microfarad, and this next one right to it, next to it, is also, is it a 47 as well? I think it is. 10 microfarad.
Okay, so this next one's 10. So this one should be 10.
And
look at this. That's a 10 microfarad. So this was
47. Right, and this one here is supposed to be a 10.
That may be our problem. Let's just measure them for ESR.
Okay, so this one here, 1.3, that's a 47, that's a little high, I think. No, it's not actually. It's a 16 volt, it's rated at 1.6, I'm coming at 1.3. What about this one here? 0.0, okay, that one's looking good.
ESR wise, but that one there, the capacity was way off. Let's just look and see if it's shorted.
$1K. Oh, sorry. May help if I measure. 0.7 ohms.
That looks like it's got a DC short. Let's change it. A new little 10 microfarad here. Just waiting for my soldering iron to warm up. We'll pull the other one out and replace it.
So that's this one right here. C407.
So that's the original one. It's an Elna 16 volt 10 microfarad. I mean, it doesn't look like it's leaking or anything. Look at the base of it, it looks okay. Anyway, I'm going to put this one in. Put that one in place of it. Okay, new capacitor is installed. Let's power this thing up and see whether I've fixed the problem or not. Still going slow. I was sure that I was going to fix it. Well, let's continue on. Wait a minute. Might help if I plug the head back in.
includes no salt, phosphates, pumice,
Fixed it! Cool.
borax, or other agents.
There was the problem.
Works is
I'm going to shut the sound off on this thing so we don't have to listen to that going. Incidentally, this was a video that I did for Works Environmentally Friendly Cleaners. That's one of my videos. Works Clean and Gentle. I did a couple for these guys. I've got another one too. I should find that one. Okay, let's see what the signal looks like now. We'll put the scope on and see what we've got going into that chip and coming out of the chip. See whether we have a nice clean signal now. Okay, there's our pulse. That's what we're looking for. That's the one that was just noise before, right? When I was checking the pins on the chip. It's actually the output from the chip. Yeah, that's I had nothing on any of the pins before. I just had noise, and now I've got a nice clean signal, and this unit is playing back just fine. So there it is. Now you know what to do. Well, you know, one of the things that can cause a failure of the control track is it's not always the head. It's not always the head is dirty or the head has failed. Sometimes you'll get a component that'll fail. In this case, it had a capacitor that, even though it looked okay measuring ESR doesn't tell you the whole story. You have to look for a DC short as well, and look at the capacitance of it, because that'll usually tell you. See, everyone thinks, okay, I'm just going to test capacitors with my ESR meter, and if my ESR meter shows me that they have low equivalent series resistance, that they're going to be fine. The problem is how an ESR meter works is it's not actually measuring the capacitance, and it's not measuring for any shorts between the two plates, the foil plates. Inside a capacitor, what makes up a capacitor is this might be easier if I grab a piece of paper and kind of draw it out for you guys to understand. Inside a capacitor, you've got two metal plates, two strips of foil, and in between them is an insulation material that's soaked with the electrolytic, or if it's a mylar capacitor, it would be like a strip of mylar between these two plates. Paper capacitors used a piece of paper between the two of them. Dry paper in most cases. These are the high voltage ones from the old tube radios. But you've got these metal plates, and if I open up this defective cap, we can see what's inside it. And these metal plates are separated by the insulation material. The job of the insulation material is to keep the plates out of physical contact with each other. But in close enough proximity so that AC signals can pass between the two of them. So basically what happens is your positive form on this plate and your negative electrons form on this plate, and they're kept physically isolated from each other by this insulation material, the dielectric as it's called. But as you know, like charges repel each other, and unlike charges attract each other. So electrons are always wanting to get across here to go towards the positive plate, but they can't because the dielectric in between is preventing them from crossing over the plate. If you feed an AC signal in here, or into the side, it doesn't matter, the constantly changing signal will have an influence on what's on the other side, because when the waveform becomes positive on this side, now you've got a plus charge here, and the plus charge will push the electrons on this side out, and then when this one goes back negative or vice versa, and you've got a negative charge on here, they're going to attract the electrons back towards the plate, but they're kept isolated from each other. So there's no physical connection. Unlike a resistor, which a resistor is just a piece of fine wire, and it restricts the flow of electrons. So if you've got a bunch of electrons here, right? They're under high pressure. Think of it like restricting the pressure on your hose, and going through this very small restriction, you've got just a small amount getting through. That's what a resistor is. But a capacitor doesn't do that to an AC signal. A capacitor acts like a dead short for an AC signal. All those electrons arriving and being replaced by protons as the AC signal is changing polarity up and down, they are influencing this other plate because the two of them are in close proximity to each other. And that is how a capacitor will pass an AC signal but block a DC signal, because this insulation material here blocks the signal but allows an AC signal to pass through. And when you're measuring ESR, what you're doing is you're applying a signal of around 100 kilohertz to one of the plates. And of course that high frequency signal is going to pass right through as if this insulator is not even there. It's going to behave as a dead short. And the better the dielectric, which is the electrolytic that's on the insulation material, the dielectric, the better that the electrolyte is, the more electrons are going to pass through from one side to the other. And that is how an electrolytic capacitor works. Well, all capacitors work, but electrolytics are the larger value. And that's how your ESR meter works too. When you measure ESR, I'm just trying to open this thing up carefully without cutting myself. When you measure ESR, what you're doing is you're forcing an AC signal into the capacitor, into one of the terminals, and that AC signal is going to influence the plate on the other side because of induction. That's what the word I was looking for. Induction from one plate to the other. Now if I can pull this thing apart, we can unravel it, and I can probably get a carcinogen on my fingers. I don't know what's in this capacitor. It's certainly not going to be PCBs, but I'm sure it's water-based, this one. Most of them are water-based now. It's either water-based or fish oil-based. This one's proving to be a little bit more of a challenge to open up. But open it we will, in the name of science, as the guy across the pond would say. Open it we will, in the name of science. Oh, wait a minute. I forgot one thing. I'm poking fun at someone right now, okay? Gotta have that prominently displayed. Gotta have that prominently displayed on my channel, right? To make it authentic. Because in the name of science, we're going to open this capacitor up, and by gosh, we're going to see what's inside it. So there's the case. And this is the rubber plug. And this is what happened on a lot of those leaky caps, is that the electrolytic actually ate through the rubber plug. Either the rubber plug itself wasn't heavy enough, or more likely what caused it was that the electrolytic that was put in them was caustic. It went base from the pH change from being in a charged versus a discharged state. We'll just clip those leads off. Maybe I can pull this cap off now, this plug, so that we can get a look at the actual makeup. I should have picked a bigger capacitor. You think I could have picked a smaller one to take apart? I just picked the one that was dead in this machine. Not that we're going to see why it's dead, but you never know, right? Take the tape off that's holding it together. It's basically wrapped up, and if I can break through that
covering, I can unravel the capacitor, the foil plates. Am I on camera? Might help if I do this on camera, right? Okay, so there we go. Now, as you can see, we will unravel the two plates. And here is what I was talking about, right? Here are the plates. And as you can see, one of them is connected to the one electrode. And if we peel this one back, I should be able to open that up a little more here. If we peel this one back, you will see that there is the insulation material that separates the two plates, and this is what forms an electrolytic capacitor. A couple metal plates, very thin metal plates, and the size of the capacitor as far as the capacity goes will determine how wide the plates are and how long the foil is. So when you get a capacitor such as this one here, well, this is going to have many more times. This is a 200 volt rated capacitor, so it's going to have a heavier insulation material between them to withstand that higher voltage. So instead of the paper being, or this is like a fabric, I guess, the membrane, or maybe it's paper, but probably paper. It looks like it's paper. It just comes apart just like that, right? But this is going to have a thicker dielectric between them. The plates themselves won't necessarily be that much longer because this is only 82 microfarads. Same with this one over here. This one's 33 microfarads at 450 volts. So capacitor is physically larger, right? But the actual plate material themselves, the metal plate, is still going to be very thin, and it's not going to be not much longer than this one here because the capacity is based on the actual physical size of the metal plate. The longer the metal plate, the more electrons can be stored on them. But the higher voltage ones require a heavier dielectric that goes between them to withstand the higher voltage. And that's why when you look at the ESR on high voltage capacitors, the ESR is always a lot higher than it is on low voltage capacitors, because the actual membrane that's between them, this paper or fabric membrane, whatever they're using, is heavier, which provides a higher ESR, higher equivalent series resistance, when you pass that AC signal through. But anyway, somewhere in this unit here, this capacitor, somewhere these plates shorted together. When they shorted together like they did, well, they're still going to test good when you test ESR, because the ESR is just looking at the equivalent series resistance passing an AC signal. And passing an AC signal is what a capacitor does. So the lower the ESR, the better. That means that the electrolytic, the liquid compound that's on the insulation material, which could be oil-based or water-based, but that means that the insulation material is still good. And what happens is, when a capacitor starts to fail, the electrolytic starts to dry up. And as it dries up, it becomes a better insulator, and it doesn't allow those electrons to get pushed from one plate to the other to influence the other plate to pass the signal through. Because it's all about this being fairly passive as far as allowing electrons to push their way through, while still physically isolating them from each other. So when the dielectric insulation dries out, the ESR will start to creep up, and then the capacitor is considered shot at that point. But in this case, that didn't happen. What happened actually had a physical short between the two plates, and that is what killed the capacitor on this unit. Anyway, I hope you guys learned something, and this machine is now back in service. I'm not making any money on this, because a machine like this you could buy at the Value Village for 20 bucks. So if I make 20 bucks to fix this, it was brought to me by a neighbor, but if I make 20 bucks to fix this thing, I'm lucky, right? But hey, it's a neat old machine that is saved from the garbage can, and now it's operational again. So hope you guys enjoyed this one. we'll catch you in the next one real soon. Bye for now.